All right. I hope everybody can hear me. So first of all, I would start by thanking the organizers for providing me this opportunity to talk about something that I'm really excited about currently. And I also like to thank all of you for staying here, listening to my talk. So this is a work that I'm currently doing with Taroknath Maiti, who is present in the audience, Akash Kumar Shah, who is also present in the audience, and Sagnik Mondol, who is an undergraduate student at ISC. Tarok is a postdoc, Akash is a PhD student. This is a work in preparation, so I would really appreciate your comments. So the idea here is I'll try to convince you that using high energy neutrino observations from the sun can be used as a discovery tool for dark matter electron scattering. Like you can discover dark matter electron scattering using this observation. So this is a slide. I'll give you a one slide introduction to dark matter for people who are not familiar with it or who don't think about it every day. Then I'll be talking about dark matter electron coupling, which is the coupling that I'll focus on during this talk. I'll be talking of dark matter capture. Okay, I'll be talking about capture of dark matter inside the sun using via scattering with electrons, and then I'll be talking about how you can use the high energy neutrino observations of the sun by the ice cube telescope to probe dark matter electron scattering cross section, and then I'll conclude. Okay, so this is a one slide introduction to dark matter. This obviously is a busy slide. I intentionally made it busy because I want to tell you that there is lots of observations of dark matter, starting at the galactic scales from the rotation curves to scales slightly larger than the galaxy, like basically looking at the motion of the dwarf galaxies, going to the scales of galaxy clusters, and then also finally going to the CMB scales, right? So this whole scale spans from kiloparsec to gigaparsec, right? So there's 6 orders of magnitude, where if you do almost any astrophysical or cosmological observations, you need dark matter to explain your observations, right? And if you are a theorist, you still need dark matter. You can try to simulate the universe on your laptop. There are some programs which you can literally run on your laptop, and you will see that if you want to reproduce the observables in the universe, you need to have dark matter, right? So let's proceed. So although we have discovered dark matter for many decades, I mean, next decade will be 100 years of discovery of dark matter by Fritz Zwicky, yet we still do not know the very basic question: what is dark matter, right? So if it's a particle, and if it makes up order 1 fraction of the dark matter density, then its mass can be as light as 10 power minus 22 eV. If it's a compact object or an astrophysical object, and if it makes up, say, order 10 or 1% of the dark matter density, its mass can be as heavy as 100 solar mass, right? So this is roughly 80 orders of magnitude, right? And we still do not know where is dark matter, right? And I think the thing that I want to at least impress you during this talk is that it is important to thoroughly test all well-motivated candidates, irrespective of various theory biases. Theory biases are great. They are lampposts towards looking at something, but it's also useful to use all observations that we have to find dark matter, right? So it's important to test all regions of the dark matter parameter space and various different couplings of dark matter and small particles, okay? So we will be considering, or we will be discussing dark matter electron coupling. So this is a study which has really taken off during the last decade, right? Both in the theory perspective and in the experimental perspective. The idea here is as follows, especially in terrestrial experiments. You keep your detector in underground lab so that you can shield it from various backgrounds. You hope that at some point a dark matter particle will come, will scatter electron, and then you will try to search for the recoil of this electron, right? So something that this atom will do when you ionize it, and you try to search for this coupling, search for this signature, all right? So typically, you can do the kinematics, and you will find that this is generally sensitive to lower dark matter masses as compared to nuclear scattering, right? And the next slide, I will show you how low. And there are many ongoing and near future laboratory experiments trying to pursue this strategy, right? For example, the Sensei, Xenon, various versions of Xenon, Darkside 50, CDMS, Edelweiss, Dumic. And as I said, there have been tremendous progress, both in the theory perspective and the experimental perspective. So this is what the landscape looks like for dark matter electron scattering, right? This plot. So what is plotted on the x-axis is the dark matter mass in MeV, and what is plotted on the y-axis is the dark matter electron scattering cross-section in centimeter square. This is for something called FDM equal to 1, which shows that there is not much momentum dependence in the scattering. In case you're not familiar with these plots, anything that you see shaded is ruled out, all right? So that means if you take a dark matter mass of 100 MeV, take cross-section of 10 power minus 37 centimeters square, that's ruled out. That cannot be It cannot be the dark matter coupling. So there are various elements that we use for searching this. So this sensei search is done by a target of silicon. These have the smallest target masses. However, they have the lowest dark matter mass threshold. So in fact, they are the most sensitive to dark matter mass of 10 MeV, right? So you can see this thing, this is minimum at 10 MeV, roughly, all right? That's what I mean by most sensitive. Then you have argon. So these have mid-range target masses and have mid-range dark matter thresholds. So this is for dark side 50 and dark side 50. There are two versions of this experiment, right? Depends on how they did the analysis. They are most sensitive to dark matter mass of 50 MeV. So you see this peak is roughly 50 MeV, all right? And then there is xenon, which have the largest target masses. However, they also have the heaviest dark matter mass threshold. So this is for xenon 10, Panda X, and xenon 1T. So these are various experiments of xenon using from various collaborations. They are most sensitive to dark matter mass of 200 MeV. So this one is peak. I mean, the most sensitive is 200 MeV. Note that for nuclear scattering, this most sensitive region is roughly 30, 40 GeV. All right. So that's what I mean by if you use electron scattering, you are sensitive to much lower masses. However, I would like to say that this is a plot which assumes the standard halo model of dark matter velocity distribution. That may not be the case. In fact, if you look at recent Gaia data, Lamos data, various sky survey data, it tells you that the local stellar halo has substructures. It's not smooth. And that also means that most probably dark matter in the local volume must have substructures. So there's this work that I did with Tarok, which looks at dark matter substructures for xenon-based detectors. And you can also think of what will happen if the smooth halo velocity distribution is different. So this is a work done by Tarok, Tirtha, and Shambho, where they look at the modifications of these constraints due to various modifications in the halo velocity distributions. Right. And there are many other literature on this. Just catch me if you want to learn more about this. Okay, so if you look at this plot, one of the questions you can ask is how to probe heavier dark matter masses. All right. So this plot stops at 1 GeV. What about 10 GeV? What about 100 GeV? Yeah, you can ask this question. Turns out that all of these constraints just linearly scale with high masses, right? 1 over m chi scaling. So the kinematics is exactly the same, except that the number of dark matter particles that is hitting your detector falls off as 1 over m chi, and thus these law just linearly just extrapolate. You can just do this. All right. So then you can ask, well, is there a way to improve our sensitivity to higher masses, right? You may think initially it's a simple question to answer. Yes, obviously increase the exposure, right? You build bigger detectors of these instruments and run it for a longer time, and then you will find that you will either discover dark matter electron scattering, or you will rule out many large regions of parameter space. So these are some of the exposures that I was talking about. So just to give a scale, dark side has an exposure of 12,000 kilogram days, Sensei has an exposure of 20 gram days, and xenon 1 ton has an exposure of 22 ton days. Right? Again, the question is, can we do better? The answer is yes. We can use the sun to do better. And I must acknowledge Tarok, who actually first pointed out this possibility to me. So the sun, as a dark matter detector, has orders of magnitude larger exposure. It has been moving through a dark matter halo for its entire life, right? The sun's age is roughly a few gigayears. The mass is obviously 1 solar mass by definition. So the exposure is 4.6 m solar gigayear. Look at these exposures. These are like orders of magnitude smaller, right? So that tells you that this is by the just target mass times lifetime. This tells you that you can use the sun as a dark matter detector, right? And this is something I'll talk about. First thing that you have to first understand is how do dark matter particles interact with the sun? This is a sort of an old topic. And then the second point is how do we detect the signature of dark matter inside the sun? Okay, great. So do dark matter particles interact with the sun? So the answer is yes. For proton targets, this has been studied since 1986, first by Andrew Gould. So the idea is as follows. Suppose there's a dark matter particle at a distance far enough away from the sun. It obviously has a velocity which follows the velocity distribution in that region of the halo. It gets gravitationally attracted towards the sun. You can do the simple kinematics. The velocity as it enters the sun will be square root of u chi square plus vsk square. This is the standard thing we learn in school. Then it can go inside the sun. It turns out if it has a non-negligible dark matter electron scattering cross section, there is a possibility that it may sometimes it may scatter with the electrons inside the sun. Once it scatters inside the electron of the sun, there is another possibility that this is a 2-to-2 process. All right, dark matter electron goes to dark matter electron. Right. So there is a possibility you can do the kinematics, and there is a possibility that the final state, the final velocity of the dark matter after scattering is less than the escape velocity of the sun. Once it happens, the dark matter particle gets captured. Right? So this happens for a small fraction of the dark matter particles. Right? And thus, using this process, using this scattering inside the sun, scattering with solar electrons, dark matter particles can get captured inside the sun. Okay, so this is what is the capture rate? So this is a long formula. You don't have to worry about it. Obviously, it depends on the total number of electrons inside the sun. It obviously depends on the incident dark matter flux. Depends on the dark matter electron scattering cross section. And it depends on the capture probability. Basically, what is the probability that after scattering it will have a velocity less than the escape velocity, right? And you can do a very order of magnitude calculation. Suppose you assume m chi equal to 100 GeV, all right, and sigma e equal to 10 power minus 39 centimeters square. The total amount of dark matter particles captured inside the sun is roughly 10 power minus 17 solar mass. How big is that? This is similar to the mass of some asteroids we have. So it's a huge amount of dark matter inside the sun, right? Huge amount of dark matter inside the sun can be captured. So now what? So is there a signature of dark matter inside the sun? So one of the signatures that we will be focusing on is basically given by this Feynman diagram process, where you have two asymptotic dark matter states and two Stern-Model asymptotic states. Depending on which way you look at this diagram, if you look from left to right, this is two dark matter particles annihilating to two Stern-Model particles. If you look at right to left, it is two Stern-Model particles annihilating to two dark matter particles. And then if you look at bottom to top, there's a dark matter Stern-Model scattering cross section, right? So I've convinced you, or hopefully convinced you, that the solar capture looks at this diagram in this direction, all right, bottom to top. Then what? Well, you can also look at this diagram in this way. So these dark matter particles, which are captured inside the sun, as I said, there's a lot of dark matter inside the sun, 10 power minus 17 solar mass. I mean, you obviously scales with mass and coupling, but at least that's a rough number you can think of. These dark matter particles, which are concentrated inside the sun, in fact, they're concentrated near the core of the sun. This is something which you can show. They can annihilate and produce various standard model particles. So the question is there a measurable effect of these captured dark matter particles? Or in other words, can we detect the signature of dark matter inside the sun? So what can come out of the sun? Turns out that the only things which can come out from the center of the sun are neutrinos, right? Neutrinos can travel from the center of the sun. Note that the neutrinos that we'll be talking about are much higher than the standard solar neutrinos, right? So they have energies much greater than MeV, mega electron volt, right? So just to give you some scale, just to make you understand things. So the solar core density is 150 gram per cubic centimeter, and its radius is roughly 1/10 the solar radius, 1/10 or 1/5, something roughly like that. So you can calculate the mean free path inside solar core of a neutrino, of a 100 GeV neutrino. Take an energy 100 GeV neutrino, calculate the mean free path. It's roughly of the order of the solar core radius, right? You can do the same thing for the antineutrino. It's again roughly of the order of solar core radius. So that tells you the sun, the density inside the sun is so high that even neutrinos can get captured, right? Even neutrinos do not travel freely, especially these high energy neutrinos, right? However, that also tells you that these are the only particles which can ever escape from the sun, right? There's a possibility of these particles escape from the sun, right? And thus, neutrinos and antineutrinos are the only particles which can inform us about the dark matter velocity, dark matter annihilation signature inside the solar core. Okay. So how will the neutrinos come from? So this is a very old topic. It has, yes. Yes, so it depends on whether the dark matter scattering cross section is in the optically thin limit or optically thick limit. You can actually calculate that. Most of the dark matters are near the solar core. It forms the Maxwell-Boltzmann density profile, but it's mostly captured near the solar core. Okay, it definitely gets thermalized. Now the question is whether the dark matter temperature is the same as the solar temperature or not. That's what the point I told comes in, whether it's in the optically thin limit or optically thick limit. You can calculate this. We are actually in the optically thin limit, but you can calculate this. This is actually been done by Andrew Gould. Just open the paper, you will see this. Right. Thanks. Good. Yes. Yeah. Yes, good. Okay. So in all of these things, so the question, let me rephrase the question just for people who have not understood it. So I have done solar capture using this. The question is chi goes to chi can also be a point of solar capture, self-interaction. So it turns out that if you take the self-interaction cross-section that we currently know, it's a factor 2 effect. It's not a big effect. So there's a paper by Andrew Zentner, which I can share with you. It's not a big effect. I mean, again, you can do velocity dependent, you can do mess up things, but it's an order 1 number correction. Yes. And the reason why it's an order 1 number, you may think that the cross section is huge. Sorry, let me tell you why is it not order 1. Because it's huge, but the number of dark matter targets are very small. So that's why it's an order 1 correction. It does not really matter. At least, and we are assuming 0 elastic cross section, but you can change it. It says factor of 2 difference in the answer. Okay, good. So how do you produce neutrinos? And this is something, as I said, has been done for the last, I don't know, 10 years. Basically, electroweak bremsstrahlung. All right. So what has been realized since the late 2000s is that if you have that chi goes to E plus E minus or any final state, you'll have something like a Z will come out, right? Electric bremsstrahlung, Z, W, gamma, everything will come out, all right? So this was actually first pointed out when we had the positron anomaly, Pamela, and then people have worked on this in great detail. People have worked on this for effective field theory operators, simplified models and things like that. Turns out that if the dark matter mass is sufficiently heavy, what do I mean by heavy? Dark matter mass is say greater than or equal to 500 GeV roughly. Due to electroweak corrections, these kinds of corrections, all of these things that you see, there will be large number of neutrinos and antineutrinos of all flavors produced from every final state that you can think of. All right, and there's been a large number of literature dedicated to studying these electroweak corrections. I mean, there are at least these 2 famous codes. There's a PPPC for DMID by Chieli et al. There's the HDM spectra by Bauer et al., who actually do these calculations in great detail and tell you that if you have heavy dark matter annihilation or decay, what will be the spectrum of various particles from electroweak corrections. All right, good. So how does the neutrino spectrum look? So what is plotted in this x-axis is the neutrino energy. Here in this talk, neutrino is equal to antineutrino, all right? Because ice cube cannot distinguish between them except for a specific energy, but I can talk about that later. And this is d and dE, all right, per GeV. So if 2 dark matter particles annihilate to produce E plus E minus, and then you get nu bar from electroweak processes, the spectrum is actually like this, all right? This is actually not exactly correct because remember that both PPBC and HDM spectra do this electric bremsstrahlung in vacuum. The sun, as I have convinced you, hopefully, sun is not a vacuum, right? So one has to actually see, suppose you produce a particle, whether it gets absorbed or does it emit whatever, WZ or whatever like that, right? So this is actually done in this, there's some work done by Arguelles et al. We follow that. But the bottom line is that the spectrum, there is large amount of neutrino spectrum. This is from the solar core, this spectrum, all right? And then as the neutron propagates out through the sun, as I said, it gets absorbed. And this is the spectrum leaving the sun, all right? Taking into account all these propagation effects. Propagation means absorption effects, roughly here, all right? You can show, I have this in my backup slides, that the capture rate and the annihilation rate are in equilibrium for the capture cross sections and the annihilation cross sections that we are assuming, all right? And the neutrino spectrum is basically this up to neutrino oscillation effects, right? Basically the gamma annihilation rate 4 pi d square by d and d. So that tells you, since because of this relation, the only free parameter in your problem is this capture rate, right? Which is sigma e, right? Up to some other factors. So using this technique, you can observe, hopefully discover sigma e or even constrain sigma e. So how do you detect these neutrinos? So we have a fantastic telescope which can do this. IceCube. IceCube is a kilometer cube detector. Devanjan is an expert on this thing. Basically, it's a detector in Antarctica. You go to Antarctica, you dig holes, you put photomultiplier tubes, you let the holes freeze. It has lots. These are all the details. I can go over all the details if you want. The nominal threshold of IceCube is 100 GeV. It also has an infill, or basically where basically there are lots of strings inside, called deep core, which has a threshold of 10 GeV. Right? And IceCube has been completed in May 2011, and it's taking full data. And IceCube has done fantastic work in particle astrophysics. They have discovered source of astrophysical neutrinos, and they have some of the strongest limits on new physics, BSM physics. The way you detect neutrinos in IceCube is basically the neutrino comes, it either interacts inside the detector or outside the detector, depending on which state you're talking about. Typically for muons, it can also interact outside the detector, produces a muon. The muon at these energies are long-lived. They'll go straight through the detector. They'll be moving at ultra relativistic speeds. The chain curve emission is something that can be detected by these photomultiplier tubes. That's what basically IceCube is. You can also detect nu V's and nu taus, all right? And again, if you're interested, I can talk more about this. So I'll tell you one signature of neutrinos inside IceCube. which is muon, neutrino, and anti-neutrino. Right? So this is actually a real data of ice cube. All right. So these are the strings. You can see these are very faint strings. Faint picture. These dots are PMTs. This is a muon which has gone right through ice cube. So this is the whole cross section of ice cube. All right. So this is early time. This is late time. All right. So you can see this is a track-like event. This is an upgoing muon track. Right. The interaction is this: nu mu plus n goes to muon plus n bar, and the corresponding interaction of nu mu bar. As I said, for ice cube, almost all energies except one, neutrino is equal to antineutrino. Right? They don't have a magnet. For this interaction, there is a factor of less than 2 energy resolution. And for the energies that we are talking about neutrino energy is less than 1 TeV. The angular resolution is less than equal to 5 degrees. In fact, the angular resolution even worsens at less than equal to 200 GeVs. Right? So atmospheric neutrinos all over the sky form a major background for this search. Atmospheric neutrino is cosmically hitting the atmosphere, producing neutrinos. Ice cube detects that regularly. There are billions of atmospheric neutrino data. However, you can use muon tracks to get rid of this background. Why? Atmospheric neutrinos to 0th order is isotropic. There is a angular dependence. I can talk, but let's talk later about it. So the way you do it is you can use this muon track. As I said, they have a 5-degree angular resolution, and you look at the neutrinos or the muons which are coming from ice cube, from the sun. Right? That suppresses the background. You can just do the delta omega calculation. That suppresses the background by 2 orders of magnitude immediately. Right? So you don't have to look at all sky. The second thing is atmospheric muons. Since you produce atmospheric neutrinos, you can also produce atmospheric muons. There are 2 ways to stop this. Either you use the observation of the sun. When the sun is below the horizon, muons will not go through the earth. So you can stop atmospheric muons using this. Also, you can either use starting events or deep core to mitigate these 2 backgrounds. All right? Again, this is some technical details. If you are interested, please ask me. Note that this is only one signature of ice cube. Ice cube also has other signatures of nu e's, nu taus, and even for neutral current interaction, this is charge current interaction. And all neutrino flavors are used for various search strategies of what I'll be talking about. Okay, so what are the results? So the idea is very simple. This is an idea which ice cube has actually done, right? Except that they have not probed the dark matter electron scattering using this. So this is the sun. This is the ice cube detector. Obviously, this is not in scale. Due to this dark matter annihilation inside the sun, there is a neutrino being produced. The neutrino goes through the detector. It produces a muon track, and the muon makes this angle, theta sun angle, with respect to the solar direction. The sun is 1 degree on the sky. As I said, at these energies, the angular resolution of ice cube is 5 degrees. So effectively, it's a point source for ice cube, right? So you can do this in more details. So what you can plot is the number of events in ice cube on the x-axis, and the solar opening angle, cos theta sun, on the y-axis. All right. So this is some data from atmospheric neutrinos, which ice cube has actually measured, and they have plotted it. This is from the ice cube 2016 data set. And if you have a dark matter mass of 1 TeV, and if the electron scattering cross section is 10 power minus 37 centimeters square, and if the dark matter particles analytic to tau plus tau minus, this is what you will get. This histogram, right? This is the event number due to new physics, right? So this is the direction of the sun. Right? This is the direction of the sun. So as you see, for this naive example, the number of events clearly exceed what has been observed. This is atmospheric neutron data set, which is measured extremely well, like 20% uncertainty, roughly, even if you include systematic uncertainty. Right? How does it depend on the flavor? That requires a long time to explain, but let me explain. So, okay, so this is a muon track event. So why is it a muon track? Because first of all, muons have a large lifetime, and they lose energy very little, d/dx, right? Suppose this nu e n goes to electron n prime. Electrons have obviously an infinite lifetime, but they lose energy very fast, right? It's 1 over m or 1 over m. So 1 over mass of the particle or 1 over mass of the particle square, depends on which energy loss channel you're looking at. So the electron signal looks like a cascade. It's like a sphere. So suddenly you see ice cube, suddenly there's a sphere appears in ice cube, and that's the electron signal. Taus depends on what channel you're looking at. So tau, and also the energy. If the new tau energy is less than, say, roughly, it depends on what analysis you're looking at, but to say roughly less than 1 PeV, it still is a sphere. But if it is more than a PeV, something funny happens. So the new tau comes, hits the nucleon. So a tau is produced, and this n prime is produced. This n prime gives you a hadronic shower. You can detect that. But then the tau travels for a short distance, and then the tau decays, hadronically or leptonically, whatever it is. So you get a sphere, line, sphere. So that's called a double bang event. So that's there. Yeah. So these are the various direct. This one, I mean, we have not done it. But, I mean, we have not done this. I'll show you the E plus E minus constraints. Yeah, but E plus E minus constraints, we do get weaker limits, but I'll show you. Okay, sorry, I misunderstood the question. Kept on talking. Okay, so this is your answer. So what happens if you do this, right? Do this strategy. You look at the sun, then look at real ice cube data and try to constrain this thing. So what is plotted? Yes. Yes.
So you are imagining dark matter getting captured.
Yes.
Then annihilating.
Yes.
Creating the.
Correct.
But there is also because going.
Yes.
This collision is also going to give you.
Yeah. So that's some relative velocity that is there in the calculation. That's basically relative velocity, right? That's what we're talking about. So
yeah,
if you
that electron or how the electron gets upscattered and that can be
which electron gets upscattered?
So E plus chi going into E plus chi plus 2 to 3. E plus chi going into E plus chi plus.
Wait, just 1 second. So you're talking about this process, right?
Yeah, E plus the final state.
Oh, you're talking of the you're talking of the Z Bremsstrahlung during the capture.
Not captured, it's
yeah, so that's
right.
Yeah. So this diagram in this direction you're looking at, right? Chi E goes to chi E. Yes, correct. So that is suppressed. Why? Because the center of mass energy is extremely small. You can try that. That is suppressed. Doesn't work. Here it works because the center of mass energy, we have the dark matter mass center of mass energy, which actually helps you. This direction, the center of mass energy is suppressed. Right. Good. Yes, I'm almost done. Okay, so this is constraint. Dark matter mass in GeV on the x-axis, sigma E on the y-axis. Chi goes to E plus E minus. Basically, what you do is you make this plot for chi goes to E plus E minus. This is the xenon 1T constraints, right? You just extrapolate that 1 over m chi is the constraint. And our constraint using IceCube 2016 data is this, right? So we, as you can see, we get constraints which are very competitive with xenon 1 ton. And something I'll emphasize, especially in the next slide, next thing is as follows. Suppose you have chi goes to tau plus tau minus. Again, dark matter mass on the x-axis, sigma E on the y-axis. So that means dark matter is getting captured due to electron scattering and then annihilating to tau plus tau minus. This is xenon 1T constraints. And this is the constraint that you get from the recent deep core data, 2021. And these two are constraints you get from deep core and IceCube data from 2016. This is an old constraint from Super Kamiokande by Joachim Kopp et al. You can see that if you have this annihilation channel, the constraints are orders of magnitude stronger than anything that xenon can probe. All right. These limits will improve with near future data from various IceCube upgrades, even IceCube, CAME3net, and other neutron telescope data, Hyper K, Super K, and things like that. And there is a tremendous discovery potential, right? These constraints will go down as 1 over square root T, right? These are just the atmospheric, how well you know atmospheric neutrinos. That's it. So yeah, it's 1 over square root T constraint. You can do for chi goes to nu bar. Similarly, we have constraints which are the most stringent in the world, right? In the plot of sigma E versus m chi, right? Again, this is xenon 1 ton. This is from the deep core 2021 data, and this is from deep core 2016 data. This is from deep IceCube 2016 data. Again, these are the most stringent constraints on dark matter electron scattering at these heavy masses, assuming the dark matter inside the sun gets captured and analyzed to nu bar. Again, this is guaranteed to improve. IceCube will be there. It will look at the sun by definition. IceCube is sort of like a 4 pi telescope, right? All these future telescopes are like 4 pi telescopes. They'll just run, all right? And there's a tremendous discovery potential. Even if you don't discover, all these constraints will come down as 1 over square root time. All right, so doesn't want to go to the conclusion slides for some reason. Oh, yes. Correct. So this was a question which was asked. So currently I'm assuming there is no self-interaction of dark matter. So that means dark matter is not captured due to self-scattering. Chi goes to chi. You can show that that's an order 1 effect. Why? Because although the chi goes to chi cross-section is tremendously large, it's about a barn per GeV, turns out the number of dark matter particles is much less than the number of electrons. That's why it's an order 1 effect. And there's a paper by Andrew Zettner and then other people have worked on it. It's an order 1 effect. Yeah, I'll be happy to chat more on this. Anyways, so these are my conclusions. I've hopefully convinced you that it's important to probe all new regions of dark matter parameter space and all different couplings of dark matter Sand-Mold particles. All right? We probe dark matter particles captured in the sun by electron scattering and then using the neutrinos which are produced from various dark matter annihilation final states. So for various final states, we derive the most stringent bound using real data of dark matter electron scattering cross section for heavy dark matter, right? And there is near future guaranteed data set. IceCube Gen 2 is funded. CAME3net is funded. Baikal GVD is funded. Hyper-K is funded. Right? They will be either currently running, that means IceCube, or under construction. They will guaranteed look at the sun. They cannot not look at the sun. They will by definition look at the sun. And there's a tremendous potential to discover dark matter interaction using this technique. Thank you.
Okay. Questions?
Yes.
Okay.
Yeah, sure. Go on. There's a
Okay, thanks. So this is most of a curiosity from an outsider. So I have heard a similar effort where sun is replaced by neutron star.
Right, good.
Right.
Yes.
So if dark matter is captured to a neutron stars, it basically affects the radiation that it emits, maybe the frequency of the pulsar.
Yes.
So can you make any quantitative remark why
Yes.
this is better
Yes,
than
I can
the...
make many comments. So two things.
Yeah.
So first is this technique will not work because the neutron star is very far away. The sun as a star is anomalously close to us, right? Super close to us. But you can do other things. One of the things that you're talking about is heating of the thing. So remember that dark matter, basically when it scatters, okay, I have to go too many slides, but dark matter when it scatters inside the electron or the nucleon, it transfers heat to the object. So there is this proposal of using JWST, James Webb Space Telescope, to look at the heating signature of neutron stars, of cold neutron stars. The problem with that is that requires the neutron star to be very close to us, 10 parsecs. 10 parsecs is a super close distance, and that requires the neutron star to be very old, giga-year old. We have not yet detected any neutron star like that, right? So maybe the Vera Rubin telescope, which is also called LSST, will discover those neutron stars, and if they discover those nearby neutron stars, and then JWST can point towards it. JWST is not a survey telescope. It has a very small field of view. It is very expensive. So then JWST can point at it. And if it is old, if it is a low temperature, then you can detect this thing. So that's one thing. The other signature is, for example, which I did not talk about, is if you capture enough dark matter inside the sun, inside the neutron star, the dark matter particles inside the neutron star can collapse to a black hole, and then the black hole will eat up the neutron star. So you can find, and this is something I worked on, you will find anomalous masses of black holes which are floating around. This is a search which people have not done. We just did a projection, but that will probe high dark matter masses. The JWST will probe low dark matter masses. Very roughly, right? There are some caveats here, there. I'll be happy to talk more. But this is the rough thing of neutron star searches.
Yeah. Hi,
Yes. Anyone?
yeah.
Yes, anyone.
Okay. So it was a very interesting and nice idea and very nice talk. I have a question regarding the point that what kind of model that you have in mind when you are talking about the dark matter electron interactions.
So we have not studied a model which can do this, but this is basically like for heavy dark matter coupling with electrons. In fact, if you look at the positron,
because I was worried about the relic density constraints put together with the direct search together, because my understanding is that if you just take leptophilic operators like chi-bar gamma mu chi interacting with e bar gamma mu e kind of a thing, then this actually the dark matter mass is excluded up to 500 GeVs. And the effective operator scale lambda, if you take, that is at least up to 2 TeV. I mean, this is what the usual WIMP-like calculation will tell you.
So this is, as I said, this is something we have not studied. However, if you look at all these positron anomaly papers, people have studied how to get the correct relic density. What people have not studied till yet, except two papers which talk about effective operators trying to do this, is how do you get this coupling? And that is something I think people have not worked on, and we have not looked into it. But plausibly, given that during the Pamela anomaly, people had so many models, I would assume people can probably do it.
Yeah, because this sigma E that you are calculating may be related to that particular
that's true. But yes,
so this relic density and this sigma E cannot be completely independently studied, perhaps.
Yes, so that's true. There is a certain model dependence. But why am I so excited about it? The reason is because this is the same thing which IceCube does for proton scattering, and they have the strongest constraints on dark matter proton scattering. And now they don't show it, but you can even plot various MSSM models here, which they do it. So I assume I'm probably the worst model builder in this audience, but I'm sure one of you can come up with a model which can do this. Yes. Sorry, didn't answer the question. Yes.
Hi.
Yes, hi. Yeah.
Yes, sorry, just a comment as an answer to Shubhaditya's question is that we have done a work on this kind of model where the dark matter decays to, this is called a leptophilic or a flavored, lepton-flavored dark matter, where the coupling is mediated via triplet scalars. So it's a type 2 seesaw kind of extended models. And we have also shown that if you have this kind of flavored coupling with leptons, and then from these neutrino spectrum or the neutrino energy that you have studied at the ice cube or deep core, you can even differentiate between the neutrino mass hierarchies, and you can tell which mass hierarchy is preferred. And this is just to mention that this work is done with the chairperson of this session.
Yes, yes, I think I know the paper. And there you are doing dark matter annihilation in the galactic center, if I remember correctly.
No, not also inside the core of the sun. So similar kind of approach. So, and if I may ask a question, so is this a complementary research? Because you are considering dark matter coupling to electrons. So is this complementary to, so you are also posing for future experiments. So is it complementary to future linear collider experiments where E plus E minus can produce this kind of dark matter?
So all the constraints on dark matter electron coupling via colliders that I've seen from lab data sort of assumes a model, right? So that becomes a model dependent statement where you have to compare, you have to assume a Lagrangian and then try to compute this sigma E and then try to see what is the signature in lab, right? That we have not done, but there are plausible reasons to say that there will be some regions of parameter space where lab data will dominate because sun is only sensitive to dark matter masses greater than roughly 4 GeV, right? Whereas at heavier masses, this constraint will dominate. So it's a complementary between colliders and this looking at the sun. Thanks.
Yeah.
Yes.
So I have like one question and one possibility, like theoretical possibility at least. So one question is like, how do you figure out like your dark matter annihilation neutrinos from the neutrinos that are actually produced by fusion from the sun's core?
Okay. So the solar neutrinos are MEV energies, mega electron volt. These neutrinos that I'm talking about, you can see the dark matter mass. Okay, let's look at this. So these neutrinos are not at MEV energies. These neutrinos are at GeV energies, more than GeV, by the way, more than 5 GeV.
So that itself sets a bound on your sensitivity.
The solar neutrino dies at boron 8 neutrinos dies at 8 MeV. HEP neutrinos dies slightly higher, but we have never detected HEP neutrinos till now. But there's no way sun will produce order 10 GeV neutrinos. Zero chance.
Okay, and like the possibility I said, like you said, like if sun is accumulating dark matter over billions of years,
yes.
So shouldn't that reflect as a difference in the solar mass itself?
Yes, 10 power minus 7.
Basically, just compute the difference between the experimentally measured solar mass from the solar mass, assuming it's purely hydrogen.
Good. Yes.
And that difference will tell you what dark matter really resides inside the core.
This is the difference. We haven't measured the sun to 10 power minus 7.
But at least that m dot, that solar mass is measured like by general relativistic.
Yeah, but it's not measured at this accuracy. I agree. What you're saying, I agree. But this is not measured at this accuracy. So you're adding more mass to the sun, but it's not this accurate. Yes.
This solar neutrino, one component, the 7 beryllium neutrino, that's very sensitive to the temperature of the core.
Correct.
I think that's T to the 17.
Good. Yes, correct.
So if you are changing the core temperature, will you already
Good.
see it in the 7 beryllium?
Yes. Okay. So the question is, we are producing we are putting non-conducting particles inside the sun, right? Obviously, the sun will change. This is how the first solar neutrino problem was trying to be solved by Preston-Spergel. Turns out, basically, if you use helioseismic data or heliospheric data, those constraints, we have not done it for electrons. For protons, is actually very weak. For protons, these constraints from ice cube are much stronger. So if you, so your point of having non-conducting particles inside the sun, and how does it change heliospheric data, helioseismic data? It actually gives a weaker constraint. Yes, but as far as I know, it actually yes. What you're saying, it works. Except that it is not, okay, for proton scattering, I don't know about electron scattering. For proton scattering, the constraints are weaker. That's the only thing I'm trying to say. At some point, it will actually have a strong constraint. Now, for the proton scattering, all the xenon and even ice cube, these constraints are weak. But it is an effect. It is an effect. There it is an effect. Although it's a very small number of dark matter particles, it is an effect because of exactly the thing that you're talking about, because the temperature is the neutrino is very sensitive to the solar temperature. Yeah, so we don't know about what happens for electrons, but we think it will be weak, simply because for protons it is weak.
Okay, so there is a question from Poonam Mehta. Can you hear us, Poonam?
Yes, I
You
can.
ask now.
Yeah. My question was roughly related to what Shubhaditya was saying, basically. So, because there are constraints and one has to connect to relic density, and
Yes.
it seems that in the region of parameter space where you are setting constraints, you have not shown any other constraints
Yes,
on
because
the plot.
yes,
So,
because model independently,
how to-
this is the only constraint in this part, xenon 1 time.
Mhm,
Right.
mhm,
So again,
mhm.
this depends on the model. This is a good question. It depends on the model, and this is something which I have not been able to figure out. But model independently, this.
But
xenon
somewhere one has to like connect the two things together, right?
Yes, agreed. Yes,
Yeah.
agreed. Yes. So somewhere one needs to take a model, but depends on which model you're looking at, whether you're looking at
Absolutely.
simplified models or effective operator models. One needs to connect it. But this is something which we are, which maybe is a thing of future work.
Okay, so
Okay,
last question.
thanks.
This this prescription, it also talks about this Earth and the Moon as well, probably, if I remember. So
Correct.
to check for the Earth, because
Good.
I mean, also another, I mean, just to connect to this point, because with Sun, there is always this proposal of this solar atmospheric neutrinos, which can be also in this very high
Good.
range.
Good. Okay. Two questions. Let me first answer. For the Earth, the exposure is very small. The Earth is 10⁻⁶ solar mass, and the Earth is not as old as the Sun. So that kills it immediately. That's one thing. Second thing, the Earth is not a good reason is because in Sun you can point. Sun is moving. Earth you cannot point. You have to look at the whole 4 pi or 2 pi. That's a background dominated search. So you can do the same thing, not this. You can do the same thing for protons. The Earth constraints are much weaker.
Probably in the Earth, it's more close towards the core. So
yes, correct.
You have
Does
a
it
better
work?
directionality.
It still doesn't work actually. It still is weaker.
Already checked it, yeah.
Yes, this is. I mean, I have not checked it, but for protons, this is a well-known result. For protons, the Earth constraints are very weak. What was the second question? I forgot.
This was regarding the solar atmospheric neutrino.
Yes, good.
Be a probable background for.
Yes. So solar atmospheric neutrino means cosmic rays coming in, hitting the sun's atmosphere, producing high energy neutrinos. These are exactly in this energy range, right? I mean, make this into energy. This is exactly in this energy range. Turns out that the corresponding cross sections is orders of magnitude smaller for this thing, right? So solar atmospheric neutrinos in addition to atmospheric backgrounds, solar atmospheric neutrinos will also be a background, but that's smaller than this. It's somewhere here, right? So it's currently, given this constraints, it's not a stop, but it's not a showstopper. But at some point, people will find that. So it's like I think the flux is 2 orders of magnitude smaller than what ice cube sees currently, as far as I remember.
In comment, because like in most of this, I mean, these are like for different channels, and probably you are taking the branching ratios to be exactly one for all these different.
Yes. This you can scale. Then it becomes just a linear scaling.
Yeah.
Yes.
So I mean, the other possibilities could also be there. Like
yes, you can have a mixture of these things. That's why I showed nu bar tau plus tau minus e plus c minus. You can have actually, for example, when people do this in the MSSM, they actually have a mixture of these things. And as I said, our motivation is even there, you still get the best limits on dark matter, proton spin dependent scattering. So we think this can actually be a good option.
So I think afterwards. So there's a last question from Rohini.
Yes.
Just a minor question.
Yes.
You're showing, for example, I can understand the thing going up.
Yes.
That is because you showed us other plot with the
Absorption.
that
Yes.
I understand. What is the idea of increasing, decreasing upper limit
Yeah.
at lower masses?
This one.
Uh,
Oh, so this is ice cube threshold is roughly 100 GeV. So that's why this goes up.
oh, it is just the effect of the threshold.
Deep core threshold is lower, so that's why it goes.
No, it is just the effect of
Yeah, just threshold, yeah, nothing else. So you can see that super K can look at very low masses. Even deep core can look at low masses. It's just threshold thing.
So
Nothing
it
special.
is just the threshold.
Yes.
Okay, so let us thank the speaker.
Okay, thanks.